We present PVT++, a simple framework for end-to-end predictive visual tracking. Standard visual tracking is conducted in an offline setting, where the trackers are assumed to have zero latency. However, the onboard latency can't be neglected during online tracking when deployed on intelligent robots like UAV. To be more specific, as shown in the figure, the tracker's results are always outdated and non-real-time trackers could skip some frames. Compared with the offline setting, the online setting can make most trackers struggle according to our experiments. To compensate for onboard latency, predictive trackers need to output future states using a predictor module. Compared with existing predictive trackers using Kalman filters, we propose a new framework termed PVT++. PVT++ is trained on common video clips but can effectively generalize to complex and challenging UAV tracking scenarios. Besides, it incorporates the existing tracker's visual feature for robust prediction. Moreover, to avoid introducing extra latency, PVT++ is lightweight and quite efficient. With these designs, PVT++ achieves significant performance gain on various trackers in the online setting. We next introduce 3 insights in PVT++. To enable a generalizable framework, we present relative motion factor as training objective. To be specific, we first calculate the averaged history motion speed as PF and assume the object is undergoing uniform linear motion. Then, we use the predictor network to estimate the correction on this uniform motion assumption as the final prediction, which we named the relative motion factor. Since relative motion is usually independent of the absolute motion, such a design can avoid overfitting to the training setting and generalize to unseen, complex motions. How to effectively utilize the pre-existing tracker's visual feature is the second insight in PVT++. We discover 2 optimization keys. First, auxiliary motion supervision is needed on the tracker's visual feature so that it can be used to predict future motion. Second, the tracker module needs to be unfrozen in early epochs with a small learning rate for joint optimization with the predictor. We finally display the lightweight network design of the predictor module. It consists of independent feature encoders and temporal interactors for motion and visual branches. After the interaction, we use a shared predictive decoder to get the relative motions. These network layers can have extremely small channels, so that it introduced very few extra latency on board. We present some qualitative results here. As base trackers have a mismatch with the ground truth due to their latency, PVT++ can effectively make accurate predictions. Compared with Kalman filters, PVT++ is better at scenarios where the object undergoes viewpoint change and in-plane rotation. We attribute such superiority to the incorporated visual features, which can be naturally utilized to predict the future state of objects. Thanks for watching.